Okay, good morning, everyone. We are back for day 4 of the Senior Project Lab Symposium, and today we will be having a half day of presentations up till noon. possibly 4 presentations. We're still trying to confirm one last presentation. But as far as I know, that should be, well, as I find out, we'll let everybody know. We'll follow the schedule as it is laid out. So we've just spent the last short week seeing some pretty amazing presentations, and I guess today we're going to be lined up to see some more interesting and amazing presentations. So again, thanking everybody that participated, whether you're a observer or you're the actual presenters. Thank you. It's quite inspiring, especially for the students that do all this hard work, to have an audience that's just not their own cohorts or peers. It's people from outside of interest. So once again, thank you. So this morning we are going to start with Fleber Zimmerman. By his reaction, I didn't get his last name right. He's been trying to train me all the year to get it right, and I always forget, so he can correct me. So Fleber, are you ready to go?
Yes, it's a man.
So how is it again? So I can say it properly again.
Ximenez.
Say it again, one more time.
Ximenez.
Ximenez. Okay.
Yeah, S-H.
Yeah, I'll forget again.
No problem. It's okay. I think we lost Mr. Metcalf.
Oh, there you go. Sorry about that. You can go ahead there if you're ready to go. Anytime.
Okay. Thank you. So I think I have to share my screen. Share content. Okay, can everybody see my presentation?
Yes, yeah, we see it.
Okay, let's start. So, good morning, everyone. I am Fleber Ximenez, and today I'm gonna present you my senior project, which is remote utility control using LoRa. So I would like to thank everybody for the time you have taken to watch our presentations today, and especially our instructors for their patience and dedication to while helping us with our project. So before we start my presentations, I want to introduce you to the term LoRa, because I think most of you are asking yourselves, what exactly is LoRa? So LoRa technology, it stands for the name LoRa. It stands for long range, so LoRa, and it is a wireless and low power technology for data transmission. So information, you share information via RF, and that uses license-free frequencies in Canada, specifically in the US, North America. This here is a picture of the chip you're using for our project, and we can connect device to device, device to gateway, or any kind of connections, and horizontally and vertically in terms of hierarchy. And we can use for Internet of Things, which is a pretty much a common term nowadays. And the technology promises up to 5 kilometers coverage in the urban area and up to 15 kilometers in the suburban area. So I can transmit and data over long distances with low power consumption. So here is the overview of the presentation. So we gotta go through the motivation for the project. I'm gonna show you my block diagram, and we will discuss a little bit my pseudocode for the project, my concept drawing, the schematics, which is really important part. The final version, I were able to finish the project, and the challenges faced during the project development. Sorry about that. Motivations. So I'm from a oil industry background, and here is an example of a oil storage or part of a refinery plant. So in that time, or as you can see, the tanks and the equipment is all spread over the place. So it's geographically really spread out. So it's not concentrated as in a factory or in industry. So this kind of industry, there is a strong need to control something that's remotely located, and control and monitor a load, a pump, or any kind of equipment. And it does require long cables and complex installations because the equipment is located too far from the control center, and the cables have to run for kilometers sometimes, and it passes through manholes, handholds, and any wiring box. So, and as you can see, it's an open environment here, and the animals, they like to make their nests inside the manholes and handholds, and it's specifically rodents. They like to they like to bite and chew the cables. So in my background, we had a lot of problems dealing with faulty cable circuits. So in my project, my intention is to remote control and operate, and monitor as well a load remotely by using the RF link that the LoRa technology provides. So we are gonna prove the concept by controlling and monitoring a DC load remotely by using this RF and wireless WAN technology. So let's move forward. Here is my block diagram. So as we have a remote part and two different parts, one is located on the load side and the other one is located on the operator side. So here I have the load that I want to monitor and control. And on this side, here, measure unit, the load, and the remote unit, the other side, remotely installed, is my operator in the control center. So we're gonna go over the two sections. So as we need to separate the project in at least two sections, and we're gonna go over the two sections of the block diagram. So the remote unit, so the operator side, and when I monitor and when I control the load. So the volt regulator, we had to power our system, our circuit, our board, and I have the power input, which is made by a jack connector. I'm using, in this case, in our project, a AC wall adapter to connect the power input that goes to a voltage regulator, which conditions the voltage to 3.3 volts and 800 milliamps, specifically the one we are using in our project, that powers everything on the board, including the MCU, which is the brain of the controlling part, and the MCU, based on the inputs, the MCU controls the operation of the circuit. We have the LoRa module up here in the center, which is our transceiver. The LoRa module is actually technically is a transceiver, able to receive and transmit messages and via RF. So we have our RF connection, so we need RF to transmit the data. So we have a SMA connector and a antenna, a quarter wave antenna, 950 megahertz, with both SMA and antenna with a 50 ohm impedance characteristics. We have the buttons. So by pressing the buttons, I can oscillate my remote unit from, actually I toggle my remote unit from the operating mode and the measuring and monitoring mode. So either monitoring or operating mode, it's all controlled by the MCU based on the button inputs. And as you can see, we have the mode button and we have the operation button. So the system starts up at the monitoring mode, and when I press the mode button, I change the system to the operation mode. And if I press the operation button, and the system will operate the load, turning on and off, depending on the previous state. So based on the inputs, my system change its behavior. And the LCD, so the LCD is the interface between what is happening on the system with the operator. The measure unit, it is the block diagram for the measure unit. You see, we have the MCU, the LoRa module, and the RF connection, and the voltage regulator similar. They have the same functions. So the MCU controls the process steps and everything. But now we have a status LED, which shows on the load side the state of the power switch, which controls the load. And the power switch is a photo MOSFET, a optocoupler, and which contains an LED and a photo MOSFET inside. So, and the current sensor measures the load current. So measures the load, the current is the load actually. So the current sensor measures the load, and the output is a voltage signal from zero to the maximum voltage in our case is 2 volts, but it converts the current into a voltage signal, which is measured by the MCU and transmitted to the remote unit. But we're going to go over this later, explaining the system functionality. So here's the pseudocode. So the pseudocode, the remote unit, and the measuring unit as well, it's basically a state machine. So while in monitoring mode, even if I press the operating button, the system won't do anything related to operating the load. So here you see, every time I press on the top of the pseudocode, every time I press the button, the mode button, I change the mode variable, and causing the system to go to to toggle between monitoring and operating mode. And while in monitoring mode, I only read the load current message from the measure unit. And how do I read this message? So the LoRa module is it communicates with the MCU via a UART interface. So when I want to transmit a message, I send a command to the LoRa module as an ASCII commands. So while I send these ASCII commands with my information as an ASCII format, the LoRa module does the transmission to the via RF to the other unit. So, and I can read on the other side as an ASCII commands as well. So we can go over this later, the code, the message. So the state machine is based on pin change interrupts. So the interruptions I use for its PC interrupt 0 for toggling the mode, and PC interrupt 1 for the while in operating mode for the operation button. Every time I press the operation button in operating mode, I have this interruption doing something on the system. And the UART1 is connected to the LoRa on my MCU. Here, the MCU, actually here, the MCU, this MCU has two UART interface. So one is connected to the LoRa module to transmit and receive data. And the second one is connected to the LCD. So the LCD also receives message via a serial interface, so I can display my message on to the operator. And also here, when I operate the load, you can see the if when I operate the load by pressing the operation button, it is not a trivial message. It sends a message and waits for the confirmation from the LoRa module on the measure unit side. So we will see this later more in detail. So here is the pseudocode for the measure unit, which is a state machine as well, and it toggles the states from the transmitting mode and receiving mode by a timer overflow. So a timer overflows and it changes the mode of the measure unit. So in one mode, I transmit the current value to the remote unit, and in the other mode, I wait for a load status operating message from the remote unit, which only does that when I operate properly. So we have to how can I say that? We have to toggle in case we have an operation, but it doesn't mean every time it will read a message. So it goes back to the transmitting mode. We control the LED as well. So as you can see, if the load status message is on here, I have the power switch is on. I lit the LED inside the optocoupler, and I change from green. So my LEDs, it's a dual color LED. So when the LED is lit green, it means this power switch is off, and when the LED is lit red, it means the power switch is on. So the code controls this state changing. And now it is my concept drawing for the remote unit, and you can see the mode button here, the operation button, the power connector for the jack adapter it's underneath the cover, so you can connect on the bottom, and the LCD screen, the antenna, as we mentioned before. And we can see the tip of the connector. The measure unit, which is a pretty much similar in terms of the RF part. The power connector is similar, and the two load connectors. So I need to connect my load to the measure unit, And also the ground, so the measuring unit and the load ground has to be connected as well, but we will see a little bit later. Here is the, probably you see on the document package that I sent a different version of it, because it was there is a typo on the previous version, and I correct. And this is how we connect the load power supply to the measure unit, how we connect the load, and how we connect the ground. So the rated current is 4 amps, and the rated voltage is 12 volts. So let's move ahead. So the schematics. Here's the one of the most important parts of the project. Here is the lower module on the right, receiving data and the reset command as well at the startup of the system, and the TX-RX interface with the one of the UART on the MCU, which is on the center. And here we have the 2 push buttons combined with a debouncing circuit, and also the in-circuit serial programming. And on the bottom, we have the power input and the voltage regulator. On the measure unit, as mentioned before, the dual color LED, the power switch, and the current sensor, and the 3 connections to the load and to the ground. The lower module, again, the UART and the reset, the MCU controlling everything, and the in-circuit connector as well for allow me to program my MCU. And here is the final version. So we were able to finish the project, not the way we did some issues. We had some issues, and we'll discuss later. So the mode button, the operation button, the LCD and antenna and power jack connector. The measure unit already connected to the load and to the power source. So the status LED here, you see on my demonstration how it operates. And challenges. So the LoRa module requires some particular PCB design and fabrication process. So to achieve the 5 kilometers and the 50 kilometers range, and to everything work properly as it's RF, the impedance have to follow the requirements. And we had some issues on transmitting and receiving messages. It has more fails than usual, but it does the job. It only takes longer than we expected due to the PCB limitations in terms of the fabrication process. We couldn't reproduce the requirements that the manufacturer of the LoRa module requires for a perfect functional behavior. And as I mentioned, RF transmission, we have not the performance the technology provides, but we already know we couldn't reproduce, so we know that we would have some issues. And the final testing, due to the COVID-19 restrictions, we weren't able to final tests as we planned, but it's going to be performed after the symposium and probably next week, and we will be able to add the final testing results as an addendum to the final report. So in conclusion to the first part of the presentation is this technology and this project of remote monitoring and control can be scalable. We can pretty much reproduce in large scale to provide a solution for the market, for the industry using this. And Also, it's versatile. As you could see, I convert the current in the voltage signal via the current sensor. I could convert anything in a voltage, as any sensor does. It just convert into current or voltage signal, and I can adapt. We can adapt the project to any applications. It's affordable, and the cost of the 2 units was about $200 Canadian dollars, and in terms of price, it's really it's affordable for even for small companies to develop such a solution. It's efficient, so it's a low power consumption, and we are talking in terms of milliamps consumptions in 3.3 volts. So, and we know that it's low power. And it's modernization. We can reduce a lot of problems and issues by just adding this new technology to our industrial applications. But here are my sources and that I used to produce the presentation. And now I'm going to change to my demonstration. So start sharing. And let me change my camera. So I think you are able to see my setup with my my remote unit placed here and the measure unit placed over there. Here's a multimeter measuring the load current, from the measure the load, and a load box simulating the load. A resistive load is simulated by this load box, this decade box. And on the bottom here, I have a power supply, which is the source for the load, the decade box, and the 2 setups. I'm gonna power up the system now, and just give me a second. So as you can see, the measure unit is on, and the LED is green. So the standard state for the LED and the power switch is off. If I have a voltage sag, or a loss of power, I turn off everything. And my remote unit showing the value of the current, it's in amps, so you can see it's showing 0, but sometimes the communication fails and the system shows a current loss message because, as we mentioned before, the communication fails. So now I'm gonna operate the load, so it's showing 0 amps here, and it's every time the signal is lost, it shows that the message of lost current. And here's the current 0, so matching with the ammeter. Now I'm gonna operate my remote unit to switch the load on. So I press the mode button, and you see the load state message here on the top. So I'm gonna operate the load to the on state. It's gonna take a while, so you can see my setup here with the LED. So the LED changed to a red color, and we can see current on the load. And the remote unit is now waiting for the confirmation message from the measure unit. It takes a while due to the communication problem, but it helps. So now we can see load status on, and when I change to the monitoring mode again, and as soon as I get the message of current on the remote unit, it's current loss, so I can see 0.1 amps, which is close to 0.15 amps shown on the ammeter. If I vary the load here, I'm gonna change the load. I can measure current variation on the as soon as I get the message again, the current message. So it's 0.2 now, which is it's not too close, but it's within the accepted, because our resolution is 0.1 amp, so 100 milliamps. And now I'm gonna turn off the load. So I change to the operating mode again, and I operate the load by pressing the operating button. You see the LED turn to green again in a couple of seconds. Yeah, it's green again. The load current is 0, and it's gonna wait for the confirmation message. Take some time. Yeah, load status off again, and that's it. That's basically what the project does. And so thank you. I'm open to questions right now. So thanks for your time. And
all right, Flubber.
Let me change my camera. Sorry.
Sure. Too many of me on screen there.
Yeah. Sorry about that.
No, that's fine. That's fine. We'll give you a few seconds for that.
Yeah. Can you hear me now?
Yes. Great presentation. Great demonstration. I'll just ask. I'll just ask one quick question, or actually two of them, and then I'll leave the floor open to other people if they want to ask questions. Can you bring up your schematic?
Yes, for sure. Let me put on there.
Sure. And while you're doing that, I'll ask you my second question that has nothing to do with the schematic. Why didn't you at any point when you're displaying the current on your device, why didn't you include the units for the current? Because you mentioned several times, it's displaying in amps.
Yes.
You know, with today's display technology and microcontrollers and that, it's easy to add an A at the end of it, right? So was there a reason why you?
To be honest, I simply forgot to do that.
Okay, all right.
It's not a problem. You're right, Mr. Metcalf. It's
That's right.
really simple to implement.
Quick firmware update, and you'll be off and going, right?
Yeah. I was afraid of, change anything on the project because I already submitted. But you're right. It's simple. It's simple to implement this solution.
Yeah, you could have updated things between the last time we evaluated. Now that doesn't matter.
Yeah, it's one of my dilemmas during this.
All right. Could you show me the other schematic for the other unit? That's the one I'm...
The measuring.
No, actually, no. Yeah, the measuring. Yeah, that's right. The one you had there. Yeah, sorry. K1, which is an optocoupler, right?
Yes.
Why did you go with an optocoupler there? What were the reasons you went with an optocoupler?
Well, at the beginning of the project, I was deciding to not have a electrical. I wanted to isolate the load from the measure unit source, which I changed over the time. But I decided to keep the optocoupler because we could. I didn't want to deal with electromechanical relays, so I decided to keep the optocoupler.
Oh yeah, but you didn't have to go to electromechanical. I mean, a MOSFET or anything like that would have done a switching mechanism too. My question really was what you alluded to at the start, where you're looking to isolate. Because if you were looking to isolate, your circuit fails at that. Because from the optocoupler, you're tying into your current sensor, which is not isolated galvanically, and then TB2 brings a ground in from your circuit too, right? So there's the lack of galvanic isolation is obviously apparent there. So
it was defeated for sure.
Yeah, all right. Well, that's fine. Again, the optocoupler was a solution that worked for you. It's not typically the solution we use it for in the case that we don't want isolation, but that's fine.
There is another reason, Mr. Metcalf.
Okay, go for it.
I was planning to work with AC at the beginning as well.
Okay.
And a photo triac would be a better solution if it was AC, but...
Oh, yeah. All right. No, that's good. I was curious because if your answer was because you wanted the isolation, I was going to point out to you that wasn't going to happen.
It was defeated. It was.
All right.
Yeah.
Okay. Right on. It's again leftovers from your previous design iterations, right? That's what it amounts to. All right. I'll give other people opportunity to ask questions, and I'll come back there. We'll talk about the RF section a little bit later there.
All right.
Well, since we're on the subject of the schematics here, what software did you use to draw your schematics, Flipper?
This is the Eagle. I draw on Eagle, and we can add a frame and everything. Mm-hmm. And I did basically everything concerning the schematics Eagle. You may have a later version of the schematics, so it's on the presentation. I updated the symbology for my jumpers.
Oh, right. Okay, yeah, I see that.
And yeah, basically, sorry about that. Just the jumpers. I forgot to update the symbols.
What I wanted to address was that there's several little formatting issues, and to me they're standing out like a sore thumb. Like I'm looking at where your R1 and R2 is, that point where the two resistors and the capacitor meet up, like the capacitor is not lining up.
Okay.
Exactly. And I see for your A1 IC, your pin 6 and 7, there's a little blip there too.
Yes, there is.
And on your other schematic, there was a couple. They're just like minor flaws, but to me they stand out. I see like where your power jack is coming in, C7.
Yes.
It's not lined up properly there. Your VDD for your A3, I see they're not lining up there either. But it's just like, maybe you didn't notice those things, but I noticed them right off the bat. So just keep your formatting clean, I guess.
Yeah, I think the other thing that maybe has to be, and this is not just for you, Flipper, but when you are submitting documents for evaluation, and at the start we obviously are very picky on the editorial side of things. Okay. If you choose to revamp or restart your drawings, and again, I'm not being particular to you, Fleber, I'm being particular to everybody because we've seen a lot of this. If you choose to revamp or redo your drawings, I know my expectation, and I'm sure is that you're going to apply what was told previously for changes, so that even if you are again starting anew or whatever, you're not going to have the same errors as you had previously, right? Okay, so we're trying to impart on you guys some best practices.
Okay, I understand that.
I'll just ask a little bit further here, not to take away from Denise' time here, but just quickly, is this? Did you take a screen capture of this, or
Yes?
because you know what, it's very, very fuzzy, and if you were presenting this on an overhead for a crowd, I don't think people would see anything at all of information. You definitely could not read. Even here, I noticed that the capacitors and so on, they're all very blurry, and there's no space between the plates or anything like that. And then I look at the one you provided to us, all right, which is a very much a nice, cleaner document, and I understand it's because it's a PDF, but the reality is PowerPoint takes in various drawing options too, right? Not everything should be a screen capture, because the problem with a screen capture is as soon as you change resolutions on anything, it becomes horrible. Okay, so again, I'm telling you this, but I hope the whole audience that the people that are the students are listening to, and whether you've presented or are going to present, be aware of that, because that has been a comment that instructors have been talking about between ourselves, and we've said a lot of what we saw on as presentation displays would not work in an overhead in a face-to-face presentation.
But I'll just re-emphasize that a little bit. If you can use vectored graphics as much as possible, and like as soon as you rasterize it, you're losing information. Like I can't see it at all. And if you're on the stream, it's even worse, right? Because that process happens again. So it kind of degrades twice then, right? So just thought I'd point out that for the people on the stream, it's it's important for them to be able to make out the printing.
Let's not forget. Oh, sorry. I just want to say, let's not forget, this is part of your communicating with people. Okay, and if you were to put up, for example, a document with text, and it was full of typos, we'd be all upset. But that's the same thing with this. It's a communication, right? There's 1,000 words here. It's an image, right? It's 1,000 words. That old adage. Well, you want to make sure those 1,000 words are well written, right?
Okay.
A couple of quick questions on the technology, Laura.
Yes.
I found this a great presentation, very interesting. Unlicensed, how do you deal with interference issues? Like, do you have software control over frequency bands you use, send and receive?
Well, the LoRa technology does have some embedded coding and decoding. It's kind of inside the module itself, and it's what I read from the data sheet. And as it is low power, I think they find a way to manage the interference side. But what I could read from the data sheet is that they have internal coding and decoding and multiplexing and demultiplexing stuff to prevent a signal that is not from a similar LoRa module.
So does maybe frequency hopping is built into the frequency management or spectrum management or spread spectrum? Or
they use FSK modulation to transmit, but I didn't go into more depth.
Second quick question. I assume this will handle multiple field units, right? If you're talking about your your tank farm, you would probably have a central unit and multiple slaves or remotes?
Yes, it is possible too.
Is
It
there
is possible.
any limits that you're aware of?
Well, this LoRa module, they have a channel separation. You can enable that feature on the LoRa module. So you put each sensor or remote terminal unit, RTO, on one channel, and it doesn't get information or interferes with another channel. So I didn't use it because I only have one.
I understand.
Yeah, but it is available on this chip specifically. Channels.
Very useful technology
Yeah,
application. Thank you, Flubber.
yeah, no problem. No.
Can I I want to follow up a little bit on Don's first question. Did you need any kind of licensing requirement?
No, I went through the data sheet and the regulation part, and they said if you meet this following requirements for power and antennas, you can use without asking permission. So
okay, who it does need to be licensed actually, but not by you, right? So who needs to license this device?
Well, the frequency usage in Canada is licensed by ICC. I think I forgot the
Industry. Well, what was it formerly Industry Canada? Okay, but that's fine. But they're the ones that managed the spectrum. Okay, but you can buy this device like you did and not have to worry about the licensing because
Yes.
who took care of that?
The manufacturer.
There you go. That's why these and Bluetooth modules, they're all becoming very, very popular because you don't have to, if you were to build this module, the internals of this module yourself, you would have to go all kinds of testing and certification from the formerly Industry Canada. Okay, but now because the certifications and all that are done by this manufacturer, when you buy them, that's part of the price you're paying, is that as long as you follow their installation requirements, it will meet the requirements of the certification, and you don't have to buy. So it's an unlicensed. It's working in an unlicensed band with certified equipment, right? Because in Canada, you can't just willy-nilly build a transmitter and start transmitting like you want. There are very strict requirements for that, and they tend to be quite expensive if you want to get into that. So to alleviate that, that's how these modules are very, very popular nowadays because of that. The Wi-Fi modules, the Bluetooths, the LoRa's, and all these are because of exactly that. It's taking away responsibility from the person like you that's manufacturing a unit, but you're paying for it by buying the unit already made from another manufacturer, right? That's you're paying for it indirectly, right?
Yeah.
And the units incorporate the spectrum management required to contend for bandwidth.
Exactly.
Yeah. This is why it's so expensive. Each module, if we compare the price of the parts to build the project, for sure after the enclosures, the transceivers are the most expensive parts.
But you're buying peace of mind.
Yeah, you're right. Yeah. Intellectual property. Yes.
There you go. Anybody else have questions?
Thank you, Flubber.
No problem.
Yeah.
Good job.
Thanks, Flubber.
Thank you.
Good presentation.
Yeah, you're welcome, all of you.
Okay, we will take our 10-minute break, finish some administrative duties for the panel, and then we'll return right after with Mr. Caleb Campbell's solar air collector performance analysis at 9:30. So please join us then. Okay, we're back, and it's 9:30. So Flubber started off well this morning. Great presentation. We're now going to go on to Caleb Campbell's solar air collector performance analysis. Are you ready to go?
Yep.
All right, so I'll leave you the virtual floor, and you can start your presentation.
Thank you. I just want to share my screen here. Hi, everyone. My name is Caleb Campbell. I am an electrical engineering technology student at NBCC Moncton. And today I will be giving you a presentation on my solar air collector performance analysis for my senior project. And my advisor is Mr. Metcalf for this project. So my project is by taking two solar air collectors and comparing the temperature performance from when the air enters the collector to when it leaves, but I'll get into more detail about that later on. So my presentation overview. So first I'll be answering what is a solar air collector. Next, I'll be going over the goal of my project, then the key equipment that was used for my project, the testing and calibration, how data was acquired, and the final results. So first, what is a solar air collector? A solar air collector essentially is a thermal collector absorber where air enters the collector, as you can see from the air holes at the bottom. And then as the air enters, it rises and then gets heated by a solar absorber. As you can see here, this is a screen absorber, although there are many different styles that you can use. I will be comparing a aluminum screen along with aluminum can absorber. And as the air travels up, it gets heated. The temperature rises as it travels up, and by the time as it exits through a fan at the top, the temperature difference should be substantial. So this is my concept drawing. So as I said before, I have built two solar air collectors, one made of aluminum screen, the other made of aluminum cylinders. And there are two fans that are for the air exit and air holes at the bottom for the air to enter. And as you can see, there are going to be 4 temperature sensors located on each solar air collector. There will be one at the air entrance, 2 within the solar absorber, and 1 as the air exits. So as you can see, temperature sensor 1, 2, 3, 4, and it's labeled 5, 6, 7, and 8. And there will be 3 power supplies being used with my project. 2 power supplies, power supply 1 and power supply 3, are being used to power the fan, the speed of the fan at which the air exits the solar air collector. And power supply number 2 powers the temperature sensors. There's also a data acquisition unit, which gathers all the temperature sensor readings that is displayed in an analog output voltage. And from there, the readings then get transferred through a USB cable to a computer where the analysis can be gathered. So here is an internal view of my solar air collectors. So as you can see, the fan is at the top, temperature sensor 1 is here, and 2 and 3 are inside of the solar air collector. Inside of the absorber material, whether it would be aluminum tubes or aluminum screen. And temperature sensor 4 is located at the air entrance. On the back, there are 2 terminal blocks located on the back where all of the wiring connections will be, and the connections for the fan, also all the connections for the temperature sensors. So here's my block diagram. As I explained before, the variable bench power supply 1 and 3 will control the speed of the fan, from which would be variable of 0 to 12 volts DC, and also with fan number 2. Bench power supply number 2 is at a 5 volt DC, but the temperature sensors that I'll be using are TMP36, and their operating range is from 2.7 volts to 5.5 volts. And from the temperature sensors, the analog output would then be communicated to the DAC, and from the DAC, it is then transferred to the computer for the analysis to be done. So here's my wiring diagram for my project. Here are the terminal blocks. As you can see, power supply 1 connects to the 2 terminal blocks at the top, which powers the fan, along with power supply 3 to the opposite collector. And power supply number 2 connects to this connection here for the positive connection, and the negative connection to be here. The white connections, the white wires, are the analog output. So as you can see here, there's 3 pins on a TMP36. Pin 1, 2, and 3. Pin 1 is the voltage input. 3 is ground, but 2 is the analog output. So with this connection, pin 2, which is the analog output, the white wires, so for example, temperature sensor 1, that wire would then be distributed to channel 1. Temperature sensor 2 would then be distributed to channel 2. And for the power and ground connections, the power supply is connected to the terminal block, but there are jumper wires for every positive connection, and also jumper wires located here to go to the opposite collector to distribute an even 5 volts. So the key equipment used for my project. As I said, I will be using I have used TMP36 to low voltage temperature sensors, an 8-channel data acquisition system, a 12-volt fan that is 1 inch thick, 2.83 inches long, and 3.15 inches wide. A computer is needed, and also solar air collectors. So now there's 2 calibrations that were done in my project. First was the airflow calibration, next was the temperature sensor calibration. But I'll talk about the airflow calibration first. So with the airflow calibration, in order to do so, I taped a plastic bag to the back of the solar air collector where the air would exit. And the reason why the airflow calibration is needed is due to the different absorber material. And so with the different absorber material, with the aluminum tubes, the air is forced to travel specifically through those tubes. With the aluminum screen, it's a lot more open where the air could travel through. Therefore, the airflow would differ. So by taping a plastic bag to the back of each collector and having it at a fixed voltage and timing how long it takes to fill the bag full of air, and then at different voltages, and by taking the average time after doing it 2 or 3 times, I was able to come up with, so the voltage is labeled here, the average time is here, and this is the aluminum cylinder collector, and this is the aluminum screen collector. As you can see, in 5 volts, it took 53 seconds for the aluminum cylinder collector to fill the bag full of air. The aluminum screen collector took 45, and these are average times as well. So 7 volts, it was done 3 times each. So on average of the 3 times that were that were recorded, 37 seconds was the average of that. And it was the same for all of the recordings. And so the average number that displays the same is when, for the airflow to be the same, an average number would be the aluminum screen collector to be at a fixed 6 volts and the aluminum cylinder collector to be at a fixed 7 volts for it to have the same airflow rate. So now I'm going to tell you about the temperature sensor, the voltage to temperature conversion. So this table is taken out of the TMP36 data sheet. And as you can see, the TMP35 does not have an offset voltage, neither does TMP36. But neither does the TMP37, my bad. But the TMP36 does, and that is the temperature sensor that I'm using. So in order to convert the voltage to degrees Celsius, it is done by taking the output voltage, subtracting it by the offset, which is labeled here, and then dividing it by the output voltage scaling. And for example, a common temperature and a common reading from the analog output is 750 millivolts. And by doing the formula, it results in 25 degrees Celsius. Now, although that is the formula, with the temperature sensors, they need to be calibrated. So the calibration test that I did with my temperature sensors, I did a boiling water test where I had a boiling pot of water and I had a thermometer inside of the boiling pot of water to measure the actual temperature. And also I had the temperature sensor in the water. And I let the temperature sensors sit in the water, just the tip of the temperature sensor, placed in the water for 2 minutes before I recorded my results so that the recording would be accurate, along with the same with the iced water test. Now for the actual calibration. As you can see, this is temperature sensor number 1 calibration. And this was done for each temperature sensor. So temperature sensor 1, the ice water value for the measured value from the actual temperature sensor, and the ice water was 1.39 degrees Celsius, the boiling water 89.04. And the actual temperature that was measured by my thermometer was minus 1.4 degrees Celsius for the ice water, and the boiling water was 101.61 degrees Celsius. Now, in order to get a calibration out of this, a slope formula was developed. So by taking the actual voltage, the difference in temperature of the actual readings, which is the measured value from the thermometer, taking the difference in temperature of that and dividing it by the difference in temperature of the actual reading from the temperature sensor, you will be able to develop a slope. And next we'll be able to find B. So B, you need to, by rearranging the formula and taking the measured temperature of the ice, multiplying it by the slope that you just developed, and taking the actual temperature of the ice. Taking the actual temperature of the ice, subtracting it by the slope that you developed, multiplied by the measured temperature of the ice from the temperature sensor. And that results in this number. So in order to check to see if it works, so this is the actual calibration. So y equals mx plus b is the main formula. I'd be taking m, and so x would be a value that the temperature sensor is reading. So as labeled down here, this is the actual reading of the temperature sensor that would be given, right? And from there, it would be placed into this formula, and this will display the actual temperature of the temperature sensor. So when gathering information, When gathering information, you can set the different time intervals. When I tried to do, you can set it to different time intervals. For this example, I did a 5-minute interval for the demo. And with this 5-minute interval, you can see the local stamp time of the 5-minute interval. And this is after the calibration. So first, in order to put in the calibration, it is all done in an Excel spreadsheet. So within the Excel spreadsheet, the calibration, the main voltage to temperature conversion is done. And from the voltage to temperature conversion, the calibration is then applied. And as you can see here, temperature sensor 1 is at the top of the collector so temperature sensor 1, the first row here is showing the aluminum screen collector. And the bottom row is showing the aluminum can collector or aluminum cylinder collector. And as you can see, the T5 and T1 are very similar. T2, T6, very similar. T3, T7, very similar. And again, these are at the very top of the collector where the air would exit. These are inside of the solar absorber. And the two here are at the air entrance. And as you can see, the results are quite similar, but there is a definite conclusion as to which solar air collector performs which solar air collector has a better temperature difference. So next, I'm going to do my demonstration. So for my demonstration, I'm first going to show you how to start recording a file, and I will then explain as the I'll explain as the demonstration moves on. So as you can see, pressing record. Naming the file demo. And as you can see here, this is set to a 5-minute interval. And as you can see, just one sec, sorry. Here is the data acquisition unit that I use. This is a DI1110. So it is an 8-channel data acquisition unit. And as you can see labeled here, the temperature sensors are labeled with the channels. So temperature sensor 1 is channel 1, temperature sensor 2, channel 2. And although it is not labeled, this is the ground wire. And a ground wire is connected, and also jumper wires connecting all the grounds together. And the opposite end of this ground wire is connected to the terminal block, which is also connected to all the temperature sensors within the terminal blocks done by other jumper wires. So these are the power supplies. This is power supply number 1, 2, and 3. And it's really hard to see, but the voltage applied as listed in the calibration, it is 6 volts for power supply number 1, and 7, as it is here, it's 7.01 volts. And my mistake, the value for the temperature for the value of the voltage output for power supply number 2 is at 4.5 volts. When I stated before that it would be 5 volts fixed, it operates the same as as I said before, the TMP36s operate between 2.7 and 5.5 volts. Let's see the wiring, different temperature sensors, locations. So as you can see here, this is temperature sensor number 1. With temperature sensor number 1, the temperature sensor is then placed into the hole that was drilled and silicone sealed so that no air would leak. And that is done for all temperature sensors. Silicone seal all around throughout the cracks. So this is the aluminum cylinder collector, and this is the aluminum screen collector. So you can see here temperature sensor number 1, temperature sensor number 2, 3, and number 4. So this is temperature sensor number 8, and 6 and 7 are unable to be seen due to them being inside of the cans, and temperature sensor number 5. And next is the conclusion. So which temperature sensor has the best temperature differential? So the aluminum cylinder collector, for the example that was given before for the 5-minute interval, it would be taking the temperature from the exit of the collector, subtracting the temperature from the entrance of the collector. And that will result in a difference in temperature of 13.7 degrees Celsius. That is how much temperature has rose from the air entering and leaving the connector. So the aluminum screen collector. So again, this is at the air exit of the collector, and this is at the air entrance. And so on average, it is about 1.3 volt or 1.3 degrees Celsius difference. But as you can see, the aluminum cylinder collector does have a bigger temperature difference compared to the aluminum screen collector. Although it is not much LV difference, it is a difference. And on average, with all the data that was collected, the temperature difference between the two collectors all averaged to be about 1.3 to 1.4 degrees Celsius. And now I'm ready for questions.
All right. Thank you, Caleb. Good presentation there, right? Demo there too. Could you bring up your airflow data table or chart?
Sure.
Okay. Yeah, great. The question I have, I guess, is you have voltages there that relate to times, all right? But when we talk about airflow, what are the units? What are the typical units for airflow? It's obviously not just time, right?
I'm not too sure.
Well, how big was your airbag that you were filling, volume-wise?
I didn't actually measure that.
Oh, okay. Because you're talking about airflow calibration, which is true. It relates to, for a same volume, it's the amount of time it takes to fill that volume. But
Yep, it was just an average size garbage bag, and I definitely could have.
well, I
looked
think
up
you should have, because now my question after that is, if you go to your calculations at the end, where you're getting these temperature variations, right? But let's not forget, again, it's temperature, but when we're talking about collecting or increasing the temperature through a solar collector, what are we actually interested in? What is the physical characteristic we're interested in? I mean, temperature is a analog to that, or an equivalent to that. Okay, but what is the actual? When we talked about solar and hot water heaters, what were we always measuring? The capacity for these heaters, these collectors, to gather what?
I do believe the answer is the specific heat.
No, not specific heat. No. Specific heat is a characteristic of the air, or the water, or whatever the medium is. But a solar collector, what should be the parameter of interest?
The heat energy?
There you go. Energy. Exactly. Energy. And energy is measured in what?
Energy is measured in, with this aspect, joules.
Joules, sure. It could be joules, watt hours, right? Depending on what our final representation is. Okay. So let's just say joules. Okay. So really, your project, okay, true that you're showing delta T as end product. You're saying these collectors are raising the air by this amount of temperature, but why can you say that is the same reflection, it's the same outcome as if we were to do the comparison in energy? What's the relationship of delta T to energy?
So relationship with delta T energy, I'm just going to refer to the formula you were talking about for the heat energy.
Sure.
Where it takes the mass of the actual material multiplied by the specific heat of said material.
Sure.
And which is then multiplied by the change in temperature.
Okay, so the mass of the material. What did you use for the mass of the material?
I did not calculate it.
No. Okay, well, that's unfortunate, because I think true that you can show these as temperature, and if we assume that for all things being the same, right, that's where we can say that, right? If the mass of the air flowing in both of your collectors are the same, and we measure that by the amount of air for a given amount of time going through them, that's why you had to make sure that the air flows were the same, right? Yep. And we assume that the specific heat of both mediums of the medium is again the same, so air for both, right? So if those are all fixed and constant, then we can make the direct correlation that an increase in delta T will be proportional to the increase in energy, right?
Yep.
So
the heat
therefore,
energy calculation should have been done.
Exactly. So, and you cannot do that. You could not have done that without having your airflow values, right? So for me, it's not that your data, you have your conclusion there, and it's absolutely, their data is absolutely correct and great, but when we talk about air collectors or heat collectors, solar energy and such, we talk about energy. So we would have really liked to have seen, or I would have anyways, liked to have seen how much more energy that your aluminum cylinders collect versus the aluminum screen collector, right? In joules or watt hours or whatever energy units you want it to use, right?
Yep.
Okay. Because in the end, when you're talking about a customer installing this heater collector, at the end of the month, what is he paying for, or what is he saving?
Energy.
That's right. He's saving energy, not temperature increase. He's saving on energy, right?
Yep.
If he can save, I don't know, 100 kilowatt hours, which is a lot here, but if you can save 100 kilowatt hours in a month, well, that's less he has to pay to the utility, and that's a dollar sign value there, right? But if you told him, I can, my collector can increase the temperature by 13 degrees or 12, that really doesn't mean much, right? It means a lot to us, the people working the system or whatever, but as far as the end product confirming which one is better, you're better off talking about energy.
Yep, I completely agree.
Okay, so again, good analysis. Just I would have liked to have seen a little bit of the background, the proof, the this is how we get to that interpretation, right? Okay.
Yep.
Anything else?
Yeah, perhaps just to carry on that line of thought or discussion. I'm not familiar with your stated objectives from your formal proposal, but if it was to perform a comparative analysis, I think you did very well. Because you took the time and you showed us how that you established uniform conditions, the standard conditions under which, assuming the construction looked very similar, they were operated side by side in the same day. You took care to establish uniformity in airflow, calibrated your temperature senses, and so that part was very well done. But to Mr. Metcalf's point, if I look at the title of your project, evaluating and reporting, it would have been great to see thermal energy output.
Yep, I agree.
And we've tried that a couple of times. We've done that in the past, and it's what I like. I liked your airbag, taping the airbag to the exhaust duct. That may sound crude, but you know what? We've done some searching and of many methods of how to best calibrate airflow or measure airflow. That's a perfect solution for a comparative analysis.
And honestly, when Mr. Metcalf first told me, I said, "Really? Is there not a better way?" And he said that's the most common one to use, and it works very best.
We have hot wire anemometers that we purchased in past years, so you could have done a quantitative analysis.
Oh, okay.
But you know what? It would not have provided any more satisfactory results for your comparative analysis. So that's great.
Okay.
We end up with too many variables in most of the other methods. Mm-hmm. So we have, again, with a bit of experience in previous projects, we've seen that we can find out the theoretical flow rates and then compare them to that method, and it actually the errors are close, But the important thing is that because you're comparing two different devices under the same conditions at the same time, they're relative to each other very close, right? So it doesn't matter. Yeah.
Yep.
So could you bring up your wiring diagram?
Sure.
Oh, great. You had approached me several times on the wiring diagram, and it's kind of funny. You look at it, and I give feedback, but then all of a sudden, I don't know why. One day you'll show it to me again, and it just happened today, and I was like, oh, why didn't I tell him that? I think just to point things out here, you have collector 1, collector 2, which are really mirror images of each other, right? Okay. Mm-hmm. I think on collector 1, you should have actually mirrored the whole thing. So on the bottom there, you didn't have all these wires running across, and it would have made your wiring diagram a little better. Again, it's too little too late for me to give you that comment today, but I just
actually That was 2 revisions ago.
Okay.
That's exactly what I did. I had it exact same. I had it mirrored the exact same as Collector 2, but then when I revised it again due to when you actually look at the collectors, right?
I see. Yeah.
They are physically like this.
Yeah. Which again, that's good that you're justifying that. I just because I was looking at it when you were explaining, and I was like, why is it that one side really looks really easy to follow, and the other side is like very nightmarish, you know? And
it did. The wiring did look a lot better when it was mirrored like this. Yeah. But then I got looking at the actual physical, and it is physically connected like this. So I get it.
I just wanted to point that out there that and again, it's kind of too late to be doing anything about it at this point, but
just to add to that too, there's like the 2 wires that are going over from collector 1 to collector 2, they're passing kind of in the middle of terminal block 3 and 4. They look like 1 wire at first, and then they diverse into 2. So
I know it's so clustered there. It's very close together. Yep. No.
I'll tell you one thing that I do appreciate, and maybe you should have considered that, is to use like kind of the bus topology for this, like the using bus techniques where you would have had, and you do have the color codes on the end there near the TB3, TB4, and so on, and you can identify them on the other side in the same manner. Right, so that would have helped you a lot too. Maybe using like common busing symbols in between there. But anyway, I it's not here to correct your drawing or anything. Just I noticed that once again, just seeing it this time around, I was like, why did that? Does anybody else have questions? I mean, I have a few there, but I'd rather other people ask.
Maybe I noticed if maybe bring up your you have an image that showed your setup with the power supplies. With the power supplies, I think you had an image, didn't you, that showed the setup?
That was in the demonstration.
Oh yeah.
So I can just.
You can bring that up.
Yep.
Okay, that'd be great. I just wanted to see that part again, if I could. I thought this turned out really well for you, actually. I found I was able to see. I know you said you couldn't get inside the enclosure of the actual thermal unit, but I thought, other than that, you were able to show everything really well.
Thank you.
Did you? You're welcome. Did you build 3 junior power supplies?
No. These the power supply number 2, which is located at the top, that is my power supply that I built in junior, and the one on the left I borrowed from Leo Avendano.
Oh, okay.
And the one on the right is borrowed from a former graduate, Joseph Bald.
Oh, is that right? Okay.
Yep.
Oh, I just, when I noticed that, I'm like, wow, 3 junior power supplies. I didn't think that anyone would take the time to actually, after they built the one, go back and build 2 more. So I was just curious about that.
Yeah.
Just a curiosity question, really. So, but I thought your presentation was well done, and that I could see like everything that you were trying to show. It turned out really well. So thank you. Yeah.
Can you add a little bit comment maybe on the importance of having the 2 collectors and the data gathering happening at the same time?
Sure. So you're referring to having both collectors in the same conditions and collecting at the exact same time?
Exactly. What was the purpose of that exactly?
So the purpose of that was so if I were to go to the beginning and look at the main image here, the main purpose of this project was to compare the solar absorbers. So in order to do that, both collectors were constructed completely identical. The only difference between the two was the solar absorber. The measurements of the solar absorber was identical, but the actual material was not. So therefore, by placing them at the same angle, under the same conditions, and recording all the temperatures at the same time, it was able to gather comparable results.
Okay, so what were you trying to minimize?
Minimize errors.
That's right. So
Yep.
you're doing this by minimizing errors, right? Exactly.
Yes.
Yeah, that's exactly what we were looking for. Can you talk a little bit too about the absorbers inside? You selected especially on the grid one, you selected its sizing very specifically, didn't you? What were you trying to make sure was the same between the cans and the?
Sure. So I first did the measurement of 5 cans horizontally and 5 cans vertically. And by doing that measurement, it resulted in exactly 13 inches wide and 24.1 inches tall. And so to have the exact, so that was the first absorber material built. And after building this and connecting it, measuring and cutting the screen to be the exact same size was done after, to ensure that the solar absorber would be the exact same size.
Okay, but do you think they are actually the same size? Because I think we had a discussion on this at one time, and you may have kind of forgotten about it, or maybe we should have revisited. I know you're looking at it and saying, listen, if I look front to this thing, here's the surface area, right? That's what you're measuring. But the reality is, it is a 3-dimensional object, is it not?
Yes, it is.
So the surface area of your can, I don't think we can say 360 degrees of it, because the tubes obviously behind do not necessarily absorb direct sunlight, right? But the front portion does, for sure. But again, it's a rounded surface, right?
Mm-hmm.
And we could always iterate that on the other collector. Well, the back doesn't absorb directly either, so we can include the back portion. So what I think one of the flaws maybe in if I wanted to punch holes in your analysis, because it's always good to have criticism. I think that you should have, and again, I think we did have this discussion way back when, but then it kind of fell on the wayside. I think you should have been considering what is the surface of one of the tubes, okay, in a 3-dimensional aspect. Multiply that by however many tubes you had, right?
Yep.
And then your screen, your aluminum screen, which again would have been a task to try to figure out, it would have been, what is the surface area of the screen? Because that's what's absorbing that energy, right? And then transferring it to the air surrounding it, right? So I think at that point, what you should have done is take maybe a square inch, figure out the overall surface area, and then multiply by whatever your overall is. And I think you would have found that your screen probably need to be bigger. Okay. And the way to fix that would have been maybe to corrugate it, have it more corrugated than flat, which might have given it better performance. Okay, so one of the things we could conclude here is maybe the actual surface area of both don't end up being the same. So maybe it is expected that the screen doesn't perform as well under the circumstances, right?
Yes, very true.
And that's that's something you add to your conclusion, so you can then warn people that are going to do this again that might have been some of the shortcomings of your project, and for them to look at that. Okay, so just again looking at it and looking at your results, which again is a one-of project. You took some data in that, but it would have to be reproduced again, and looking at the errors. I think that is one little chink in the armor of your results. Okay.
Yep, I agree.
All right, right on. So I think that's about it. unless anybody else has another question or two.
Yeah, I think that's good.
That's good.
Yeah, that's good.
Thank
Caleb.
you. Thank you,
Thank you
Caleb.
very much.
Thank you.
Thanks.
Great presentation. And we will take 15 minutes and start again at 10:30 with, I believe it's Jordan Westwell.
Yes.
Just look at my schedule here. Jordan Westwell and his electronic lockbox project. So we'll have Jordan talk all about the results of his project. So thank you, Caleb, and we'll come back at 10:30. Okay, so we're back from our break, our 10:30, our 10:15 to 10:30 break, and everything's going fine. 2 good presentations this morning, so we're going to follow up with a third one. Jordan Westwell will talk to us about his electronic lockbox project. Jordan, are you there?
I'm here.
All right, so the floor is yours.
All right. All right. Just to start, I want to thank everybody for joining me for my presentation. All the other students and instructors, thank you very much. Anybody else that's watching, thank you for attending. My name is Jordan Westwell, and I am going to be talking about my electronic lockbox. In this presentation, I will have the reason for the project, why I decided to build what I built, the concept drawing, the block diagram. I'll explain all the different pieces of, or the different functions of the block box, the schematic, following that, to talk about all the individual components. Then we'll go through the block diagram and a couple of the main functions within the code, followed by a conclusion. So the reason that I started this project is that I had somewhat of a messy work area, and that was not ideal for using small components that are used in electronics. They kind of got scattered all around, and I needed a place to put them. And also because it's kind of an open area that I'm working in, I have a cat that likes to jump up on the table and push things around with her nose. So building a box was going to be something I was going to do anyway, and I figured why not just make it more of a project and add some electronics on it, make it a little bit more secure with a pin code, and make it kind of a fun project that I also needed as well. So here's the concept drawing. On the top left, you have the top view from the lid. So position number 1, as you can see, all the positions are down here. It's the PCB housing, and it holds obviously the PCB and the wires that run along the walls to the components that are attached. So the servos are on the back, on the outside of the box, with as you can see on the side view, they're on the back on the outside, and they have a piece of wire, fishing line, that's hooked onto the top of the box here, so that when the servo motors pull down, they'll pull this wire down and lift up the lid. The battery housing is also on the back. I was going to place that on the inside, but I didn't really have a great battery pack. It's really difficult you need to put a lot of force to get the 9-volt batteries and stuff into the containers. So I didn't have the ability to secure it on the inside as well as put a lid on the outside to cover it. And my second reasoning for that is, what if the batteries died while the box was closed? That would not be good. So it's on the outside, and the push button switch, number 4, is right here, right on the top left. It's the only switch on the front, the only switch on the front. The battery pack in the back has a built-in on-off switch to control the power. Keypad is number 5, and it's just a front-facing keypad on the front wall as well. And the solenoid is number 6. It's at the top of the box. See on the side view here, it's right up at the top. And it has a little plunger that goes in and out through a loop in the lid that, when it's unlocked, the solenoid will retract, the lid will open, and thus unlocking the box. And we have the LEDs number 7. There's 6 of them. And those are the basically the user interface. Each LED has a label that tells the person using the box what function or process the box is currently operating in. But as you can see, the box itself is 8 by 8 by 6 inches tall. And the lid is actually 10 inches long, so it has a little bit of overhang on the front and a little bit more overhang on the back, but it is also 8 inches wide and it runs smoothly along the sides. So here's the block diagram. We have a 12-volt supply that supplies both, well, it supplies everything, but it directly supplies the solenoid as it needs at least 9 volts to retract properly. So we have a transistor switch that is operated by the microcontroller. When the microcontroller pushes current through the BJT switch, it opens up and the 12 volts run to the solenoid retracts. The 12-volt supply also goes to a voltage regulator, which supplies 5 volts to the microcontroller, and microcontroller controls everything else. The push-button switch has multiple functions, which is why it has the thicker line. Those are kind of a bus topology mentioned earlier. It has multiple functions, so it has a thicker line. And the number pad, UI, and servo motors have multiple connections. There's 7 connections coming out of the number pad. There's 6 connections for the LED UI, and there's actually 2 servo motors in the notes, as you can see. So there is a thicker line to represent that as well. And the microcontroller operates off 5 volts directly, and it is the powerhouse behind everything. It's a relatively simple block diagram. Most of the project involved coding and building the project. So here's the schematic. At the top, you can kind of see all the power. Top left here is all kind of contained. You have the voltage regulator. And to the panel, I actually have a different version here, 3.90. You guys have 3.85. And the only difference here is a couple of symbols have been fixed, and I've added some labels on the headers for clarity so that you know what is actually going on there. So let's take a quick look at the power section. So what we have here is the over here you have the 12-volt supply. And as I said earlier, it goes directly through the transistor into the solenoid. This was originally a 75 ohm resistor because I misread the data sheet. I thought it said it needed that for the solenoid to work when it really said that the solenoid has an internal resistance of 75 ohms. And I had already printed the PCB, so I needed to put a jumper in there to fix that situation. So from here, let's look at the voltage regulator. It is an MEZD71201A-G. It's a switching regulator. It works from anywhere from 6 volts to 24 volts, and it steps the voltage down to 5 volts out, and it can have up to 1.2 amps flowing through it without needing a heatsink, I believe is what the data sheet said. So it is supplying the microcontroller, and also it has the decoupling caps to smooth out the voltage on the input and the output if things fluctuate. We also have a decoupling capacitor at the VCC to ground for the microcontroller. Looking at the inputs now, we have the push button switch is connected directly to PB0, and there's no resistor here. There is an internal pull-up resistor that has been set for this position, and it is on this pin because it is a high priority interrupt pin, and this button operates almost entirely or entirely on the interrupt function. I'll explain that later when we get to the block diagram. Or sorry, when we get to the flowchart and the code. The keypad has 7 pins, and they're all directly connected to the microcontroller. And essentially, the keypad just provides shorts through itself to drive pins low in my situation. I'll explain that more when we get to the code as well. So it's essentially, there's 7 pins on the keypad, and they are just directly connected to the microcontroller. And those are the only 2 inputs, the keypad and the push button switch. Sorry. The outputs, we have the solenoid as mentioned earlier, and it is connected, it gets its power from the 12-volt supply. However, the MCU will provide the voltage to actually forward biased VBE so that the transistor switch opens up and the solenoid will operate. And we also have up here the LED UI. We have red, green, and yellow LEDs. All of the voltages for the LEDs, the voltage drops for the LEDs are relatively similar. So the 220 ohm resistors, it was chosen just for simplicity's sake to order a bunch of these at once to drop the cost a little bit. And so there's 6 LEDs out. Physically, in the box, the LEDs have been connected on their ground side with essentially a bus that comes back to this one pin, which goes to ground. And we have the servo, which requires more voltage than the microcontroller can output on a pin, or current, I should say. It can provide the right amount of voltage, but it can't provide the amount of current necessary to physically allow the servo motor to turn its motor. So it's connected directly to the VDD, which is the 5 volts out from the switching regulator. And as you can see, it has a somewhat large capacitor because it is a sudden current draw, which may drop the voltage from VDD. This capacitor helps alleviate that. And PB1 is a pulse width modulated pin when it's set to do so anyway. And it provides the pulses that are required to turn the servo. It has a 2 millisecond pulse width that it requires, or 2 millisecond duty cycles. So, for example, at 1.5 millisecond pulse widths or 75% duty cycle, the servo motor will be at 90 degrees. At a 1 millisecond pulse or 50% duty cycle, the servo will be at 180 degrees, and at a 100% duty cycle or 2 millisecond pulse, it'll be at 0 degrees. The servo motor is a 180 degree rotating servo, and I have it set to basically almost go to the 180 degrees, but not quite, because I didn't want the string or the fishing line that's attached to it to potentially rotate the other direction when the servo motor goes down from its very top position. And up here we have a diode that is a freewheeling diode, just in case there's any sort of reverse current from the motor shutting off. It provides a path for the current to flow through. And here is the code flowchart. I apologize to the panel, I didn't submit a flowchart. I didn't have a good one at all prepared. And hopefully you guys can see this on your screens and it's not too difficult to follow. However, there's 2 main functions. There's the main function and the interrupt function. So we'll run through the main function first, and then we'll run through the interrupt function after that. So we turn on the box, and it goes through the initialization of the main function, and then it gets to the main loop. And the first thing in the main loop is it asks, is the lid closed? Everything in this box essentially runs off whether or not the lid is closed. So if the lid is not closed, it's constantly waiting for the lid to close. And we'll get to how it closes once we get to the interrupt function. So if the lid is closed, it will then wait for inputs on the keypad for the 4-digit inputs, and it needs to then go to the if statement. After 4 digits have been input, it'll go to the if statement, do the 4 digits match, and that should say, do they match what is stored as the 4-digit pin? If it's no, the pin wrong LED will illuminate for 1 second, and then it will wait again for the pin input. So there's the 1 second is kind of a lockout because it uses the delay MS. So that while you're waiting for that 1 second, you can't do anything other than wait to input the 4 digits again. And if the 4 digits match, then the open lid function will start, the lid will open, and then it'll essentially return back to the main loop where it will say, is the lid closed? And now because the lid is open, it will keep waiting for the lid to close over and over again. In the code flowchart, or sorry, in the interrupt function, this function is called anytime the button is pressed. So as mentioned before, it doesn't have, it's not constantly waiting for the button to be pressed at the same time it's waiting for this. It's just a high priority interrupt that when it is pressed, it basically abandons what it's doing to go to this function. So the button is pressed, and then again, it asks if the lid is open, and we'll go through the no tree first. No, the lid's not open. It then asks the second question, is the box asleep or in sleep mode? If the answer is no, then it will go to sleep. And then we start all over again. The button is pressed. Is the lid open? No. Is the box asleep? Yes. It will then wake up, and then it will go right back to the main function and start everything all over again. Once again, if the button is pressed and the lid is open, we go down here, and how long was the button, or not how long, but was the button held for at least 5 seconds? No, it'll close the lid because it counts that as a quick push of the button, and then the lid will be closed, and then we go back to the same spot. If the button was held for at least 5 seconds, then it will enter pin set mode and ask for the new 4-digit code twice. So you need to put in or input the same 4 digits twice in a row. And not the same 4 digits, the same sequence of 4 digits twice in a row. If both pins matched, because it compares the two sets of inputs that have been, or it compares the two strings of numbers that have been put in, and it will set the new pin, it will flash that the new pin has been set, and then it will close the lid automatically, moving us back to the main function. And if the pins did not match, the flash, it'll flash the set pin LED numerous times, letting you know that that pin was not set, and then it will close the lid. And we'll go back to the main function again. So if we take a look at the code, I'm going to show you the main code is acquiring the 4 digits, and then I'll show you the interrupt function as well. So here we have the keypad initialization. So how the keypad works is you need to set the data direction for what port the pin, the keypad is set to. Because when you press a button on the pin, it actually shorts either a row pin and a column pin together. And that's the basic principle about how the keypad works. So when you press a button, it shorts 2 pins together, and then you have to basically read which pins got shorted in order to figure out which button was pressed, because every button has a unique combination, as you can see down here, of which pins were shorted. So when it initializes the rows, the row pins as high, and the column pins as low. So when you press the button, it will, so when you press the button, it will delay 50 milliseconds for a debounce, and then it will scan the keypad because this is what the binary value of all 8 pins. The first pin here has no connection on anything in this circuit. So it's just going to stay 1 the whole time, as you can see. However, when you press the button, it shorts 2 pins together, one from the row and one from the column. And because they're shorted together, it'll drive one of these 1 values to a 0. So then it sets your key press code to the this value plus the 0 that'll be in here. Switch the pins to the opposite values so that now the columns are set to the input or to the output, and the rows are set to input. We do that by toggling all of these. This small delay here was a tricky find to fix, because when I was switching it and reading it again, it was coming up with the same value. It was only getting the 1 0. So what this does is it's a small delay, but it's not a delay. It essentially reads this as a line of code that has no function instead of just skipping over like an empty line would or a comment would. So it provides a really tiny delay, which allows for the pins to actually be set. And then it scans it again. It ANDs it with the first result so that you'll end up with zeros in both the row and column sections. And then I have the matrix if'd out here for all the buttons. And as you can see, I allowed the pound sign and the asterisk to be used as well for whatever reason you wanted to. They just they have a value of 11 and 12. I'm not sure why I set the button 0 as 10, but it could be set for 0 as well. And I have it set to switch back at the end, which isn't really necessary because it can go from columns to inputs, or inputs to or you can go from columns to rows or rows to columns. It doesn't really matter which direction you go, but I put that back there so it's kind of always going in the same direction. And as long as the value's been changed, it'll return the number to the main function. And that's how it receives the code that you input into the keypad. Here's the interrupt function. Essentially, it's asking if pin B has been changed, and that if the button's been pressed and the open state is 1, the 50 millisecond delay is for the debounce. And then basically while you're holding the button down, this variable will increase. It's kind of a rudimentary timer. I couldn't get a real timer to work for whatever reason. I just need to put some more time into that. And it will open, or if the timer was less than that 16 integer that it counted to, it will close the lid because it thinks it was a short press, and then it will reset the timer. And if the pin was held down for longer than that value, which is roughly about 4 seconds to 5 seconds, it will go to the new pin mode, or the new pin function, which is essentially the same function as the one I just showed you, where it gets a single digit, but it goes through that 8 times. So every time you press it, and then it compares each pin together. And if the box was asleep, if the box was closed when it was pressed, then it will go to sleep mode. If it was awake, so sleep mode 0 means it's awake, it will then set sleep mode to 1, turn off all the LEDs, and then go to sleep. In this sleep mode, none of the keypad buttons can be pressed. The only way to wake it up is by pressing the button again. So that is how the interrupt function works. And in conclusion, this project was more difficult than I thought it was going to be, honestly. Figuring out which components work together wasn't too hard, but figuring out which components work well together is a different story. Even though there weren't too many individual components in the project, the main focus on this was actually, in my mind, getting the software running properly and usably, and making it work was the main goal. And in the end, the project did work. There are still some small hiccups. As I mentioned, the rudimentary timer and the interrupt is not perfect. It works most of the time, but sometimes it obviously it can overflow and things like that. So it is not an ideal, but it works for now. And yeah, this was a very interesting class, and I want to thank Mr. Broad for helping me the entire time. It was a difficult and stressful project, especially with time management this semester. I'm sure everybody felt that. But it was probably one of the most, it was probably the most densely packed course in terms of learning, honestly. There are so many different considerations that I hadn't thought of before starting the project that as you get more and more into the project, it's kind of overwhelming how many decisions you realize you overlooked at certain steps. But I'm happy where I ended up, and I'm happy where the project ended up, and I will now do my demonstration. So let's see here. Take this. All right, so can you guys see the box there? Yes. So I've powered on from the battery pack, and as you can see, I don't know if you guys can read the labels there, but it's now closed. As you can see with that LED, you can open it by inputting the pin. You can close it by pressing the button. And as you saw, the light changed from closed to open. And that light pops up when the pin's okay, like I said. And then you hold the button down. And as I said before, it's not perfect with the timing. Oops, anyway, I input the pin wrong, so the pin wrong LED popped up. Oops. There we go. So we're in pin set mode now. And I can input any combination of digits. Just for simplicity's sake, I'll just do 1, 2, 3, 4. I'm not sure if I pressed the 2 there. Anyway, I did. So the new pin is now set, it flashed, and it's closed again. So now I can use that new code to open the box. And when you press the button while it's asleep, or while it's closed, the LEDs turn off, and as you can see, the previous pin was 1, 2, 3, 4. Nothing happens because the product is in sleep mode. And now it's back in the awake state, and it works again. And that's it for my demonstration. I am now somewhat ready for questions, I guess.
All right. Thanks for the presentation, Jordan. It was a really good presentation. Great project there. I do have a few questions, and I'm sure the panel has some more. Could you bring up your schematic for a second?
Yes. Hold on.
Excuse me.
There we go. Okay.
Let me just. All right. I was just curious. I would personally find it somewhat difficult if I had to work on your device based on the schematic, due to the fact that you show your headers and all your connectors and that, which is great. I love the fact you have that, but you don't show what they're connected to. Do you understand what I mean? Like, for example, where the LEDs are, you don't show me how the LEDs should be connected, right? You
Okay.
mentioned them, or how the servo. You have these pin values, but you don't identify where they go to symbolically, or in the case of the servo, maybe what the pin values on the servo itself is, or
Right.
For me. I understand that if this was a schematic to do schematic capture to do your PCB board, definitely works well, right? Definitely
Right.
works. Okay, but as a documentation schematic, which is kind of what it is here, it makes it very difficult for me to follow through. I just again found that a little bit rough in that case, right?
Yeah. I have a different version that like it looks like this. Can you see that?
Yeah,
Is that kind of more what you wanted?
Oh, definitely. That would have been definitely the better version to go to, especially as a documentation to show people what's going on in that.
Okay,
By
I wasn't
all
sure if
means.
that was a more ideal.
Yeah, no, that would have been more better one. The other thing I noticed as an omission there too is I don't see. Maybe it's in front of me and I don't see it. Where's your in-circuit programming header and all that?
I don't have one actually.
Oh, so how are you gonna update the firmware?
Yeah, that'll be a bit difficult.
Yeah, that's definitely in fact that was a requirement for anybody using I'm assuming a 328 there. It's not listed as that, but okay, so that's something you're now stuck with the firmware that you have on there, right?
Yeah.
Unless you would desolder it, and that's not usually a good thing to do. All right. The other thing I want to ask here is you have diode D1 there as a snubber or a flyback diode there, whatever your choice of topology is. Can you tell me why, in the case of the servo, there's no need for the diode, or did you forget it, or?
Honestly, that was an overlook on my part.
Well, maybe you should go look at the servo. And is a servo just a straightforward motor?
As far as I'm not sure the internal workings of the servo exactly, but it's just some gears that rotate is all I know, really.
Well, yeah, but for example, if you had a regular motor there,
right,
instead, how would you make the motor turn?
By applying a voltage to it.
There you go. You'd apply a voltage to it, and you could control it via switching or whatever you want. Right. And as long as the voltage is applied to it, the motor would turn. Is that how a servo works, though?
No, it has a constant voltage to it, right? And it's when the pulse width or the pulses get applied to it.
There you go. So could you perhaps extrapolate from that what do you think is between the motor part of the servo and your interface? Do you think there's something else there?
I am not sure.
Well, I think you could say yes, right? I mean, or at least you say yes. There's circuitry in there, right? There's actually circuitry controlling. Okay. Do you think that maybe one of the things they did there was actually add that snubber diode in there too, or actually
onboard little PCB that's on board?
Yeah, because again, you might want to look into how servos work. Servos are intricate motors that have multiple coils and such, right? And we, as the user of the servo, you're not interfacing with that. You're interfacing with the electronics that controls that. Right. Okay, so a snubber diode here would have been useless because it's being protected already. Right. So, at least you hope it is, anyways. Okay, yeah. So. All right. All right. Anybody else have questions on the schematic or?
Yeah, I do. You did steal one of my questions there about the in-circuit programmer, but that's okay. For the IC itself, IC1, I see like Dennis was asking that the label for it is not shown. I do see it. It's between pin 4 and 5, 328P, which is not very a good location for that. That should be moved where it's easily readable and easy to distinguish what that IC is. But just to add to that as well, like obviously you're missing the in-circuit programmer, but you can move some of the pins around and remove any unused pins to simplify your circuit as well, because you have 4 pins there that are not connected to anything, so those could be removed. And also like the PB2, instead of having that trace crossing over all of those, you can move that pin at the top just to clean it up, clean that up a little there.
Yeah, definitely.
But I was gonna add that to the in-circuit programmer, but that's all right. Yeah, that's it for the schematic side. Did anybody else have questions on the schematic? I had a question about the flow chart there, but
okay, I just want to add to the schematic that, and this is not again pointing towards you. I think it's pointing towards the whole class. That I think your attitudes as to editorials of the schematics will change significantly when you eventually go work out there and you have to work with other people's schematics. And when you work with a bad schematic, you'll know right away how come we're so picky about schematics. Right? Information that is hard to find or not there on a schematic, and that you have to spend another 5-10 minutes, hours, whatever, trying to find because the author didn't include it. It'll change your attitude about drawing good schematics. And that again doesn't just go to you, Jordan. It goes to the whole class there. You know. So, all right, yeah, I had nothing else for the schematic. I don't know about Don or Ron.
Am I audible?
Yep.
Yeah.
Barely.
Barely.
Yeah, it's really
barely,
quiet.
Barely. How about now?
Much
There
better.
it is, yeah.
Better.
Okay. I went to local mic. You referred to Jordan, you referred to C3 and C1 as decoupling capacitors. Are those decoupling capacitors?
As far as I'm aware, they are voltage smoothing, so yes.
Well, from earlier presentations, we noted that decoupling capacitors are normally located near the power supply input pin on an IC, such as your 328. So C2, I would definitely say is a decoupling capacitor. But would you call C3 and C1 decoupling capacitors?
I mean, I guess not, but.
Okay, so if not, what is the correct term for them?
I'm some sort of ripple, but I'm not sure.
Okay, we'll let you go and look that later then. I just wanted to know if you.
Okay.
I just want to add that is actually a module. It's not like a standard IC. Your selection of capacitors differed quite a lot from what the
manufacturer recommended one is considerably larger, and I couldn't get those in time.
Well,
and all I had is these, so.
You might want to look up the reason why they needed the much bigger ones. I'd like to point out, though, one last thing about that IC. It's actually an open source hardware circuit, which is we don't see as much often. The supplier will actually provide you with the Gerber files, the schematics, and the design files for their module if you so want to roll your own. All right, just to point that out.
Also, while we're here, just a comment, I guess, is when you started to present the schematic portion of your presentation, I had so much joy inside because I was like, oh, he zoomed in. And then you stopped doing it.
Yeah.
Why didn't you keep doing that? Because
when I chose the laser pointer, it immediately zoomed out, and I couldn't zoom back in.
Oh, okay.
So I apologize for that.
Okay, I just thought, okay, well, kudos to you for your intentions to do that, because I'm following on the stream and it is so much more legible on the stream when the presenter zooms into each section of the like that.
Yeah. When I
Wow.
choose the laser pointer, for some
So
reason,
much, it makes, it's, yours weren't bad. Like it was legible, but with strain. Okay. But
Okay.
when you zoomed in, it was really clear. So I just thought that was worth mentioning. And anything else from anyone on the schematic?
That's a Microsoft feature.
Yeah, that's what Microsoft calls it.
Don't get them started.
Anyway, what about the block diagram? I have a question on that. I don't know if anybody has a question on the block diagram.
Go ahead.
Okay. On the block diagram, you had made specific mention that you had used thinner lines and then thicker lines for specific purposes. And I think you mentioned that the thicker lines were like bus lines to represent that you had like multiple connections represented there.
Right.
For example, makes a lot of sense for me on the number pad, because that's what, 12 buttons.
Yeah, 12 buttons, 7 wires.
And 7 wires, so that makes a lot of sense. The LED UI must have been, what, at least 6?
Yeah.
Yeah, and the servo was probably a few wires. There was 2 motors, actually, wasn't there?
Yeah.
Yeah, so that makes a lot of sense. But I'm wondering about the push button. There was only 1 push button, so I'm wondering why you chose the thicker designation there, the thicker line size there.
I chose that because there's multiple functions to it. It has the sleep mode that it does. It closes the box and it puts the box to sleep and wakes it up.
It just seemed to me that if the thick line was representative of multiple physical wires, that maybe using a thick line of the same line thickness to represent something else isn't really intuitive to me. It almost seems like that there's that part of that push button block there that it deceives me into thinking that there are multiple push buttons, and I came to realize that that's not the case, right? I thought maybe you could talk a little bit about the iterations that your project went through, because I think you did have multiple push buttons at one time.
Yes.
Maybe about what caused you to change that approach and how you went about that.
It was a suggestion from you, and
I'm not looking for any credit. I just want you to talk.
Yeah, no, it was. I had multiple buttons, one for each function that the buttons were supposed to do, and combining it into one button kind of made it look better on the box, and it was a very smooth design, I thought, to have one button perform multiple functions instead of 3 buttons each performing one function.
And what would that do for your, let's say you go to mass production of this and you produce 1 million of these things, what would that do to your overall production cost?
It would drop it dramatically. The button I used was $3, so
it really would, wouldn't it?
Dropping out 2 buttons of box, then yeah.
Anyway, I thought that was a good choice for you to do that. Any other questions on the block diagram? Maybe we should go to the flowchart.
Okay. Go ahead, Ron. I was going to say, we're soon out of time. I wanted to get a word in here.
We're close, yeah. Does anybody want to go to the flowchart or the code?
I had a question about the flowchart, yeah.
Okay, let's go there. I had one too.
I'd like to talk about the code after too, so maybe we want to take a few more minutes.
My first comment on the flowchart is, I wish you had included it in the document package.
Yeah.
Anyway, go ahead, Denny. I took too much time already. Go ahead and ask your question.
Well, I see like this, the device itself goes to sleep. I see that in the interrupt function, but in the main function, there's no mention that it ever goes to sleep. So does it just go on a continuous loop and stays on?
It's constantly waiting for the button to be pressed again.
So it only goes to sleep if the button is pressed?
Right.
Okay. It's a little of a strange.
I think, well, that was kind of following up for me for the code. I think that's not really a way to do it. The problem with interrupts is, and I kudos for you using interrupts
Yes.
Okay, that's definitely the way to do things. However, one of the things when we do use interrupts is you don't want to stay in the interrupt for a very long period of time. And in your case, that's what you're doing is you go into your interrupt, you put it to sleep there.
Right.
Okay, so you want to be careful. There's other ways of doing it where it would actually be asleep in your main function, and then when an interrupt happens, it takes it out of sleep, does whatever it needs, and then goes back to sleep in your main function, which is probably a more efficient way of doing it. Okay. Because the problem with doing it in the interrupt is you may end up missing something else, right? Because the interrupt is working. My other comment for me for the flow chart again is again, you're showing the interrupt function as a separate thing, which is great, but you're always showing the interrupt returning to that first part in main function. And that's not really true. An interrupt, when it occurs, can occur at any time, but when it returns, it always returns to the next line where it left off. All right. So what you do in that case is don't show an actual flow line going back to your main function. All you have to do is show an area where it says return or something like that, and just have the interrupt as a single flow chart of its own on the side, right? With all the logic you have, you've got great logic there showing it. It's just that you keep showing that the interrupt will return to the start of that main function, which is not true. It will return to where it left off, right?
Yeah, I think that's an important comment there.
That makes sense.
I do think that for what it is, though, this flowchart is very clear and easy to follow.
Yeah.
Lots of arrows. Like I've seen some where I'm wondering which direction is it going. I'm not wondering that. So that's really good. Yeah. And the code, I guess, is if there's nothing else on the flowchart.
Yes. Could we see the key scan portion of your code? You use the term, and I want to kind of ask you that term again. You said, and in fact, you have in your comment there, that series of ifs, you said there's a matrix. It's a matrix, right? So when we talk about matrix, we usually mean an array, and that's not really what you have there. You don't have an array, do you?
Yeah, no,
not exactly. No, you've got an if. Basically, what you have is an if ladder, okay? Right. Is there a better way of doing it than the if ladder, though?
There is, I think, a do function, maybe?
Not do, no. Yeah.
I'm trying to remember. There was a thing we did back in the initial programming class.
Yeah.
It's not coming to me the name of it, though.
It's the case statements, right?
Yes, case statements, yeah.
Yeah. That's actually much more efficient than a series of if statements.
Okay.
The other way is actually to do what you are hinting you're going to do is actually also an array with a series of where you vector through the array. That's as a lookup table. That's very effective too. Okay, especially in embedded. But typically, when what we have here is what's called an if ladder. When it starts getting long like this, you're going to lose a lot of your performance because it has to compare every time. And it has to go look up values to do that comparison. And the case statements and the switch case statements and the lookup vectors are usually a lot faster. The micro does that better. Okay. So that's just something to optimize your code with.
Yeah. And
also where you do the ASM volatile there for a delay. You might look into the ASM function no operation.
I saw some that had no op and some had nothing in it.
No op does the same thing. It just takes a time operation statement and just doesn't do anything, right? So, this is what it is equal to, anyways. All right, that's all I had. I don't know if anybody else. Denis, did you have anything for code?
No, it was mainly just the sleep function from the flowchart.
Yeah. All right.
Which we had.
And again, I want to say bravo for using interrupts. By all means, that's something that definitely was made your code a lot better. By all means. Yeah.
Maybe I could squeeze a couple quick notes in.
Sure.
First off, I think it might have been a function of my screen presentation, but when you ran your demo, I could hear a whir and a clunk. I associated the whir with open and the clunk with closed, but I couldn't actually see your lid moving. So I did get a peek of it at the end. So small issue. Like I say, it might have been I didn't clear a bar on my screen. Second issue is on your concept drawing. And I've seen this on a lot of concept drawings. It would have been helpful to see a front, rear, top, or whatever your views were. Would have clarified a little bit. Those are very, very small things. What I wanted to say mainly, and I believe this will be our last presentation. So I'm going to wax philosophical for 30 seconds and say, go back to your conclusion. One of the things you said that particularly caught me was you referred to this senior project as the most densely packed learning experience of the program. That struck a chord. And I agree 100%. And what we've seen over the last few days is a lot of how much learning you pack into this experience is a reflection of what you've learned, and also your approach to learning, and the seriousness with which you undertake the task set in front of you. And it's good to hear it. We sometimes, as instructors, wonder and worry if we're doing enough, if you're getting enough. So it's nice to hear that as an acknowledgement. So that's it for me. Thank you.
Thank you.
Yeah, I think that was great. In fact, I'd like to just I think we're, like we said, this is our last presentation for the day here, but I'd like to maybe ask a few of the students if you just might want to speak up a little and tell us maybe a little bit, how many hours is involved in this? I think that's something that was never really, nobody really mentioned in their presentation, but maybe we could get a few of the students, the presenters here, to say, how many hours did you spend in SPL, approximate, right? I mean,
can we start with Jordan on that, since he's the current presenter?
Yeah,
sure.
Do
you have an idea, Jordan?
During the weekend, probably I take Friday afternoons and Saturday mornings off. So weekends, probably 10 hours, 15 hours, and then probably an hour and a half a day. Just trying to go over drawings and fix little things. But yeah, so.
And that's above and beyond everything else you had for course
Yeah.
loads in those two terms. Eh?
Well, your Gantt chart should tell you, right?
Yeah. Yeah, it should, yeah.
Gotta pay
that's
more
20
attention to Gantt charts next year.
That's 20 to 25 hours a week then. Did I do that math right? Something like that?
It's a job trying to build these, that's for sure.
Yeah.
At least part of them.
Does
how
go ahead,
weeks,
Ron.
How many weeks are we talking about now? Just to put this, give an overall number then. This is the end of May, so it's basically all the month of May, all the way back to January, right? So that's, how many weeks is that? Like 20, is it 20 weeks, or am I doing the math wrong there? 5 months times, would that be what it was? 21 weeks, something like that?
Sounds about right, yeah.
Yeah, times 20 to 25 hours. So what's that, 400 or 500 hours, something like that? Does that sound right, Jordan?
Yeah, it does to me.
Wow, eh?
Yeah.
What a lot of work. Yeah.
Can we have somebody else maybe pipe up? Just give their values if they have it on hand.
Can I?
Sure, go ahead, Flipper.
Go ahead.
Well, in my case, my calculations are about 500 hours this semester, but for me, it's almost a full-time job after college. So I don't think I took any day off in my project. I just go over weekends working on, and yeah, it's kind of hard to manage the time, but it's something really significant for our careers and professional lives. It's probably changed my life forever, to be honest.
In a good way, I hope.
In a good way, yeah, for sure. I appreciate your the instructor's time and patience with someone who never worked on a project from the beginning to the end. So I really appreciate that.
And I think I'll put on top of that, and this is general for everybody. It's while dealing with COVID restrictions, right? So resources weren't always available in a timely fashion and such, and it definitely did put a lot of curveballs in the situation. So this was all done during the mostly well, for the most part, it was the orange condition for a large part of it. And yeah, it made things quite difficult. Any other student that wants to? Oh, sorry, Ron, go ahead.
Oh yeah, I just say I wouldn't necessarily brag about that you got through this during COVID, but if you got through this during COVID, this was exceptionally more difficult than normal, I would say.
Yeah. Any other student that would like to tell us how much time they spent?
Yeah, sure. I'll step up to the plate.
Sure.
For me, I wasn't very consistent in my time applied in the project. However, when it came down to the final allowable moments, I would spend absurd.
Oh, your audio dropped out.
You dropped out there, yeah.
Sound like your jack came unplugged.
Is it good now?
Oh, there it goes, yeah.
Okay, yeah, sorry. I remember for the PCB design, I quite literally spent 3 days straight because I had a lot of unanswered questions about my design, and I just was so worried about it. I just went over and over and over about it, trying to learn Eagle, and just wondering if I missed something. So if you count that, that's approximately 72 hours, give or take a few meals. I think for all the other drawings and all the other design choices, all of that adds up to hundreds of hours over the course of this entire project. But it was actually a good formative moment, I think. Gives us a perspective.
Well, that's good, because that's what it's all about, is to learn, right? Learn from all of this.
I really, if I can say, appreciate your honesty in speaking about your, I don't know, I guess you're talking a little bit about your weaknesses, or it's maybe some mistakes that you made, and how this has caused you to improve, and that is really valuable to me that you would say that.
Yeah, there's no getting around it. You have to admit and own up to it.
Well, that's good. All right, so at this point, I think that pretty much concludes the 2021 version of the Senior Project Symposium. I want to once more thank all the outside parties, the industry partners, family members, anyone that took the time to watch any amount of the presentations, and by all means, if you know the person that specifically, give them feedback on that. We will be doing this again next year, hopefully in a more face-to-face aspect of it. Although we are going to continue providing the stream, that's been valuable. We've heard from a lot of people that that's a very, very valuable to them to be able to participate, and we will definitely keep that going. If you do have constructive criticism or any kind of suggestions, please again send me an email. My email's on that invite. My email is the email that sent the invite. So just respond to that, and we will definitely take a look at it and see if we can improve our abilities to to present the hard work that all these students provided. So in the end, I'd like to thank again the presenters themselves. They all did a great job. They stood up. They took a step forward. They showed us how hard they worked, what they did. I'd like to thank all the advisors. Every one of them put in a lot of hours too, and they put in a lot of hours that I asked them to do extra stuff too. So we same as the students, we have our own course loads that we have to deal with, and at the same time we realize that SPL is a very difficult course to schedule as far as man hours. And so we work really hard at that. I'm kind of tooting our own horn here right now, but in the end, though, it's the students that count. It's the students that we saw, and I was very, very proud of every one of them. So I don't know if any of the other advisors have some other comments. Just before I cede the floor to them, one thing though. Students, stay online. We have a brief meeting afterwards that will be between all ourselves. It won't be streamed, so please do not go anywhere. Stay online. And besides that, that's it for me. If somebody else wants to mention something, that's fine.
I could just reinforce what Dennis said. I mean, I've been involved in this course for a while now. And every year is difficult, but this year was extremely difficult. And I understand how difficult that it was for the. I'm getting battery low. Please recharge warnings in my earbuds. So that's how much I've used them this week. The first time that's ever happened this week. Anyway, yeah, it's been a very difficult year for SPL. And so I applaud all of you. I don't think one thing we've missed, right, is the applause.
Yes,
so,
exactly.
That's right. At the end of every presentation, we would normally applaud everybody. So kudos to everyone who went through the course. I know there was a lot of difficult things that happened, and I won't get into the details. And we understand that, and it was difficult in different ways for us too, as instructors, to, in all that was going on. So I think we shared in some way in that difficulty all together. And so thank you for all of you who went through the course. And right,
Yeah.
It must be a huge burden off of everyone to have this course done, or mostly done. I mean, we have a few finishing touches next week to do, and but getting through these presentations, I'm sure, was everybody's feeling a lot better now. So thanks a lot. I really got a lot of the presentations. I learned a lot, and I really enjoyed them this week. Thank you.
Don? Yeah,
I'll just reaffirm, I guess. Thanks for your participation. There have been some hard lessons learned this term, I'm sure, in terms of last-minute crunches and, gosh, I should know this, I don't, or why does this thing not work? So if there's lessons in that, for example, pushing on through adversity, then that's good, right? But hopefully there's one lesson some of you may have picked up, and I hope you do, either from the past or in the near future, that think of how much of the adversity could have been avoided due to your actions or your attention or your willingness to sacrifice for a worthy cause, such as your future, your career. And I also should acknowledge, two students told us that its project is like a full-time job on top of your studies. There's also students who had to work as well, so we can't acknowledge that academically, but I just tip my hat in recognition to what it is you're doing and what you've done. So thanks.
Yeah, I think you all pretty well stated the fact that it was a difficult year. It was a new experience for me, and I feel like I learned a lot going through this process on this end anyways. And I think it was a very great experience for me and for everyone. It rekindled my spark for circuit design, and I think printing the PCB boards here in the lab was a lot of fun, and I'm looking forward to designing my own again and making some new boards, but that's more on my personal side. But it was a great experience. I think everybody learned a lot from it, and it was tough, obviously, dealing with the COVID situation. And we got through it, though. We're here, we got through it, and I think everyone did fairly well, so be proud of yourself for going through this process.
All right,
Yeah,
so thank you, everybody.
Rohan has his hand up. Can we allow Rohan to say something, or is it something that can wait till later? Or
maybe he can wait till we're just the group. Is that okay, Rohan? Or all right, we'll just wait till
it's okay. Yeah, it's not a matter.
Okay, we'll just wait till it's the group. All right, so again, thank you, everybody. We're going to end the stream in a few seconds, and please, if you're looking for a new employee for your business, please consider our graduating students. All right, they have a lot to offer. So once again, thank you on the part of EET, and we'll see you next year, if not sooner. So everybody stay healthy.